Okay, well, this is the first of the OPIW Spinoff in World Challenge presentations. Thank you all for coming. I'm putting text into the chat box right now for the beginning of the talk, and the slides and your presentation, the recording of the presentation will be online for you. I'd like to introduce myself. My name is Margaret Corbett. I'm an educational consultant on this challenge. And also Dave Hartino, who is the master of our universe. Dave, you want to give a wave? Oh, there he said hi. Okay. We also have with us Maggie Massetti, who is backing up Paul Geithner, who is a distinguished engineer from James Webb. Just in case he has problems with all of this. Paul's been with the James Webb Space Telescope project almost since the beginning, since 1997, and we're really honored to have him with us today. He's going to give you an introduction and then be ready to answer questions. So as you go along, please think about your questions, and it'll be a brief presentation, and type any questions that you have into the chat log, and that way we'll be able to keep track of them and make sure that everyone's questions get answered. You all do not have voice chat access. There's just a limited number of us who do. So all of that said, I'd like to turn things over to Paul Geithner.
Okay. Hello, everybody. Hey, Margaret. Hey, Margaret. Can you hear me? Master first. I can hear you fine. Great. Okay. Well, I'm Paul Geithner. It's a pleasure to be here. I've done this briefing, I guess, once or twice for folks in real world before, and it's pretty cool. So I'm happy to be back. I have a short presentation, pretty high level. Just wanted to talk about some of the big engineering challenges of JWST, and be very happy to answer, leave time to answer whatever questions you might have. So just go ahead and flip to the next slide here, and this is just a little about me. As Margaret said, I started working on this in 1997. I had just finished working on the second servicing mission to Hubble. I started at NASA Goddard Space Flight Center working on the Hubble Space Telescope servicing, and that was a lot of fun. So I got to work on the optical correction on the original servicing mission, and then I got to work on the second generation of science instruments that were put on Hubble on the second servicing mission. And that was a lot of fun. And then that ended in early 97, and I went to work on the James Webb Space Telescope. It was called Next Generation Space Telescope at the time. And I've had various jobs here and at the headquarters for a few years working on this program. I actually did leave NASA for a couple of years and worked at a fiber optic startup, and that was a blast. But all of us became like thousandaires, not millionaires, and the company got bought by one of our investors, and then our technology was kind of too far ahead of its time. So I ended up deciding to come back to NASA, and glad I did, because I really like working on this project. It is the scientific successor to the Hubble Space Telescope, and I think it's going to have a similar impact on science and even in the popular culture that, say, Hubble's has had. And, I've been into this stuff since I was a little kid, so I remember watching Neil Armstrong take footsteps on the moon. I was always into space and science growing up, so it's pretty cool to get to work on this machine and do what I do. So, very happy to talk to you here today. So that's just a little bit about me and how I got here. The reason we're building the James Webb Space Telescope Observatory is to do science, and that's really organized into 4 themes. It's a big general purpose observatory, and one of the main reasons it's being built is to see the very first luminous objects that formed in the universe, because we're pretty sure the Big Bang occurred about 13.8 billion years ago. And after about 380,000 years, the universe cooled off enough that it went from being a plasma, a soup of neutrons and electrons, protons and electrons and some free alpha particles, and turned into basically a 3/4 hydrogen and 1/4 helium. Although that's only 4% of the universe, because we think that most of the universe is made of dark matter and dark energy, but the ordinary matter is 3/4 hydrogen and 1/4 helium. And then for, we think, maybe the first couple 100 million years, that's pretty much all the universe was. There's a lot of dark hydrogen and helium, but gravitation is pretty dominant, and somehow, the first stars, big black holes and galaxies formed. We're not sure in what order or how quickly or exactly how that happened. We think the very first stars were really large, like 100 times the mass of the sun. And of course they were made of nothing but hydrogen and helium. They didn't have any heavier elements in them. And those first stars would have lived hard and died fast. And we built this machine to have enough sensitivity to actually see those very first stars and galaxies. And so that's one of the themes of this observatory. And if we can actually directly observe what's going on there, what actually happens, we can scientists are and continue with the cell theory, they can confirm others, develop better hypotheses, really figure out how the universe worked. Because somehow the universe went from nothing but dark hydrogen and helium to a lot of other heavier elements, and made life possible like us. And we're made of a lot of other stuff besides hydrogen and helium, and the stars are kind of the factories of the universe. They make all the heavier elements. So that's pretty cool to be able to see those first luminous objects and start to get a clue as to how the early universe was working. Sort of a continuation of that story is the second theme, which is to see how galaxies formed and evolved through the history of the universe. That's where most of the ordinary matter in the universe is organized into, is into galaxies. Galaxies are kind of clumped together, and there's a lot of empty space in between galaxies. So understanding how galaxies formed and evolved is kind of important to figure out how the universe came to be. And then the third and fourth themes are kind of closely related, and that's to see how stars and planetary systems form and evolve, because there are a lot of ideas about how that works, and that we can observe with other observatories on the ground and in space today, but there's still a lot to learn about how those processes happen. There's a lot about our solar system's history that we're not sure about. There are some hypotheses and some models, but there's still some uncertainties and still some unanswered questions, and we don't know if our solar system is common or unusual. There are a lot of other stars out there we're discovering that have planets around them, but we're not sure if our solar system is unusual. It's how it's organized or not. So we need to learn more about that. And then finally, just studying planets around other stars in our own solar system and around other stars, and searching for the conditions of life or chemistry of life and that sort of thing. So all these things we can do with a general purpose, really large telescope in space that is optimized for the infrared. So I'll go to the next slide and talk about why the James Webb Space Telescope Observatory looks like it does and what's going on with why it's infrared, all that. So it sees in the infrared because that's where the science is. All that science I was talking about in that previous slide, you actually need an infrared telescope for that. For example, the very first light that was emitted as ultraviolet and visible light by the very first stars, well, that light has been stretched by the expansion of space-time, so that today that first emitted light actually shows up to us today as infrared light. It's been redshifted. So to see the very first visible light, you actually need an infrared telescope today to see it. So that's a big reason JWST is infrared. Those other themes, really old galaxies, well, they're redshifted too. So you want an infrared telescope to see them. And then star and planet formation in the contemporary universe, where there's a lot of other heavier elements and there's dusty clouds that sort of are the leftovers from dead stars that seed the formation and the generation of new stars and planets. That dust is opaque to visible light, but the longer wavelengths infrared light will penetrate it. So we can actually peer through these dusty stellar nurseries in the nearby universe, like in our own galaxy, and with an infrared telescope we can see what's going on in there. And then lastly, a lot of every element on the periodic table and every molecule kind of has its own unique spectral fingerprint. Those atoms or molecules up, they'll emit at certain specific wavelengths, or also if you put them in between, say, a light source and you, they'll absorb at certain specific wavelengths. And every element and molecule kind of has its own unique spectral fingerprint. So by using spectroscopy, which is just spreading light in its constituent colors, kind of like a prism does, or raindrops in a rainbow, we can identify these spectral lines, and we can actually remotely do chemical analysis on, say, the atmosphere of a planet around a nearby star, and we can look for things like methane and water and carbon dioxide and carbon monoxide and free oxygen and things like that. And a lot of molecules, more complicated, longer, bigger molecules, they have more of these spectral lines in their fingerprint out at the longer infrared wavelengths than at visible wavelengths. So if you're looking for organic chemistry, you're looking for something more complicated than just hydrogen and helium emission lines or absorption lines, an infrared telescope is really good for that. So all those four themes I talked about, basically, we're screaming for a big infrared telescope that's really sensitive. So that's why it's infrared. That's where the science is. So next, this thing's really large in order to be sensitive. So when it comes to a telescope, size matters. Bigger its main optic, the more light it can collect. And that means it's more sensitive, and it can also resolve finer detail. And so bigger is always better with a telescope if you're trying to see really faint, really far away things that are really small. So to be able to resolve really small angles, because further something away is, the smaller it is. So the smaller it's, you need a really small angular resolution to see that to study its morphology. And then like the very first stars, the light from them is probably going to probably going to be intercepting like 1 photon a second with that big 25 square meter mirror, and that's so we're going to have to stare at things for a long time and have really low noise detectors and have really good mirrors and big ones to see, to detect that sort of from noise. And so that's why the telescope's really large. And then it's got to be really cold for sensitivity. So not only does the telescope and the science instruments located behind that big primary mirror have to be, the mirror has to be big and the instruments have to be really sensitive, but they have to be really cold, and that's because infrared light's basically heat radiation. Wavelength makes light just a little bit longer than visible, so we don't see it with our eyes, but you can feel it as heat. And for example, all of us with our body temperature of 37 Celsius, we peak at around 8 microns. So if you had an IR camera and you were looking around at people, they would be brightest at a wavelength of 8 microns. And so if the mirror, say, were room temperature, and it would have a really high infrared background. It's really hard to see faint things if your optics are really warm, because they would be emitting a whole bunch of infrared light themselves. It'd be kind of like trying to see a firefly when it's flying like in front of a searchlight. You're trying to look right in the searchlight and pick out the firefly. It'd be really hard. So, and also the detectors, the little electronic detector chips in the instruments themselves, since they're detecting infrared light, it's just the physics of these devices. They need to be cold to be able to detect infrared photons and convert them to electrons, and do so with a really very noiselessly, if that makes sense. Do so that the electrons that they spit out are because the infrared photon hit them, and not because it's just some random electronics noise. So you add all this stuff up, and the optics in the instruments have to be really, really cold, and the electronics have to be low noise, so that we're actually, the way we've constructed the design requirements for this observatory, we're actually background limited by re-emitted and scattered infrared light off of dust in the inner solar system, that we're that sensitive because we're this big and we're this cold. So how do we get cold? Well, you can see that segmented mirror is, that big telescope, it doesn't have a tube around it like Hubble does, or like maybe any telescopes you all own and use in your backyards. It's open, and it's got this big 5-layer diamond-shaped, tennis court size sun shield that basically shades it from the sun and the earth. And that way the telescope, because it's in the shade and facing deep space, it can radiate its heat to deep space and get very, very cold, get to the temperatures that we need, which are around 40 Kelvin or so. And we point the observatory so that the sunny side is always kind of on the bottom in this picture, and that's where we have our solar array for power, and we have our antennas for communications, and the kind of box-like thing in the middle of this image of the observatory, that's where the different computers and communications and pointing equipment and all that are. Basic housekeeping and infrastructure stuff of the observatories there, and that stays in the sunshine. And then on the shady side, that's where the telescope and science instruments are, and they get really cold. It's just like the desert. In the daytime it's scorching hot, but when it's nighttime, the skies are clear and there's not a lot of moisture in the air, and the desert can get very, very cold at night because it can just radiate its heat to space, and that's how this works. And then the last two things are the Webb telescope is really lightly deployable, and that's it can be launched economically. So the mirror, instead of being one single big mirror, the main mirror is actually 18 segments. Each segment is 6-sided, so we can tile them together. And each segment's like about almost 1.5 meters across, but when you put 18 of them together, you get about a 6.5 meter total diameter filled aperture, and by making by making the mirror in segments, we can make the segments light. We can tip tilt them in all the 6 degrees of freedom, even change their shape a little bit. Little motors, little actuators that are behind the mirror surfaces, and we can fold this thing up so it'll actually fit in a rocket, because it's in this fully deployed state, like you see it here on this slide. The observatory is almost 4 stories tall, and it covers the area of about a tennis court, so that won't fit in any rocket we have today, and it wouldn't be able to handle the rigors of launch, the mechanical loads of launch, all deployed like this. So it's designed to be, we're building it so you can stow it, so it's compact and strong in its launch configuration. Then when it gets in space and gets off the launch vehicle, it can start to deploy. And there's a lot of mechanisms involved in getting it to deploy, but we need it to be large so it can be sensitive. So that's why we have to build it. The mirrors, the main mirror has to be segmented, and all these different parts have to be able to stow and unfold. And then lastly, we're sending it to a place that's really convenient for an infrared telescope. We're sending it to Lagrange point number 2, the Sun-Earth Lagrange point number 2 point. And in any two-body gravitational problem, there's 5 of these sort of stable and metastable points where the gravity of the two bodies, in this case the Sun and the Earth, sort of work together or balance each other out to create places where things either collect or it's just real easy to get there and stay there. And there's 5 of these points, and L2 is about 1 million miles or 1.5 million kilometers opposite the Sun, away from the Earth, along the line that connects the Sun and the Earth. So it's about 1.5 million kilometers away in the midnight sky. That's a way to think of it. And if you put something out there, it's kind of easy to get there, and it's kind of easy to stay there. Although if you didn't have little rocket jets on the observatory, you would slowly drift away and just orbit the Sun on your own. But if you put something out at L2 and maintain that position there, we're actually going to be orbiting L2, not like at the L2 point. So we're going to be in this orbit around L2, and since it's a little farther away from the Sun than the Earth is, you would expect it to gradually slow down and take longer to get around the Sun, but the Earth's gravity helps pull it along, and it helps create the L2 point along with the Sun's gravity. So it's a great place to put an infrared observatory, because you got to get away from the Earth. The Earth is a big room temperature object, and unlike Hubble, which is only about 320 miles in altitude, it's in low Earth orbit, and the Earth is pretty close, so it takes up about half the sky. James Webb Space Telescope is going to be much farther away, where it looks, if you were at L2, the Earth would look the same size as the Moon does to us from here. So the Sun and the Earth would look the same size from Sun-Earth L2 point, and that's far enough away that with the sun shield to block from the Sun, and what little stray light comes from the Earth, that way it can get really cold. If we were in low Earth orbit, we wouldn't be able to get cold. We wouldn't have a stable thermal environment. So great place to go for something like this, and there are a few other space observatories out in this L2 region right now, like the Herschel Observatory and the Planck Observatory, which are European spacecraft that one sees far infrared wavelengths and the other sees millimeter wave wavelengths, and they're looking at different kinds of science. And then the WMAP satellite's out there, and it's a microwave observatory. It's looking at the echo of the Big Bang itself, for example. So it's a good place to put something like this, and that's where we're going. So that's a lot on one slide about why the James Webb Space Telescope looks like it does and why it's different. So we have a couple more slides. So I just want to talk about the toughest engineering challenges. I'm an engineer, and the phase we're in right now is building this thing and putting it together and testing it, and we intend to launch it in late 2018, and then the scientists get to use it. But this thing's taking a long time to design and develop and put together, because it's a really hard thing to do engineering-wise. Nobody's ever done anything quite like this before. So there's three really big challenges with this. And the first one's temperature. And as I mentioned, science drives the sensitivity IR background requirements. And that in turn dictates the size of the optics and the science instruments, and that they need to be cold. And that drives that open architecture I talked about, the big sun shield and being at the Sonnenfeld 2 point. Big challenge, though, is we're building it at room temperature in gravity, in air, but it's going to operate in space at weightlessness and in a vacuum, and the shady side of this observatory is going to be extremely cold. And that just adds a whole other dimension to engineering, because basically we have to, this thing's, as you know, most things shrink when they get cold. Different materials shrink differently at different rates with temperature. Sometimes they shrink real fast, and then once you get to a certain temperature, they stop shrinking. So it's complicated. It's not like they all shrink at the same rate, or that rate's constant. Different materials do different things at temperature, and by necessity, JWST is made of a lot of different materials. It's not all made of the same stuff. So everything basically, but everything has to be the right shape and in the right position at the operating temperature for, of course, everything to work correctly. When you're talking an optical system, the structure that holds the mirrors and the mirrors themselves, that they can't. Of course, they're going to change some temperature, but you have to know how much you're going to change, and it has to be very predictable and repeatable. And we have to design them and build them basically exactly wrong, so that at the cryogenic operating temperature, they're exactly the right dimensions and right shape. And that's just incredibly hard. And that relates to one of my other challenges, which is testing. But this cryogenic operating temperature just makes designing, building, and testing this machine really, really hard. So that's our biggest challenge. The next one's deployment. As I mentioned, we need higher wavelength coverage, and we need a big telescope. So we need to design this thing to stow for launch and then deploy in space. And there are a lot of mechanisms that have to work, and a lot of operations that have to go correctly. And we'll be commanding these from the ground, but there's a lot of them, and they have to be highly reliable and a pretty good degree of precision. The mechanisms that deploy the mirrors and the sun shield are one thing, but then once the mirror is all unfolded and deployed, we have those actuators that are on the back of each of those mirror segments, for example. They have a range of, they have millimeter range, total range, but they have like nanometer resolution as far as how many steps you can move the mirror. And just to give you an idea, so that this whole optical system includes all the mirrors and all the optics that are in each instrument. The total air budget, so to speak, for the optical air budget for this thing is so that it's effectively a perfect optical system, but they perfect. It's limited by physics of light itself, limited by light being a wave, so it's limited by diffraction of light waves, and not by imperfections in the optics. That means our total air budget is 150 nanometers, or 150 billionths of a meter. So if you add up all the little errors in terms of surface imperfections and deviations from a perfect mirror surface and misalignments and things like that, for all the optics in the whole train, they can't add up to more than 150 nanometers, and that's pretty tough. In fact, each of those mirror segments, it can only deviate from a perfect surface by like 20 nanometers. That's its sub-allocation of that total 150 nanometer budget. So our actuators for positioning those mirrors so that one mirror segment to another match up and they work together like one bigger. So you have one surface that all the mirrors fit. They work together and have a figure that's really accurate. You have to have actuators that can move these mirrors in the order of a millimeter, but have the resolutions down at nanometer levels. And so coming up with those mechanisms and designing them and making them really reliable, that's hard. So this whole deployment thing is hard. And then lastly, verification. We have to build this thing so it works right the first and only time in space. So there's a lot of testing as the pieces are come together. As we build up things at the box level or at the mirror segment level or at the little actuator level even, and we do a lot of testing at that level and make sure everything works at a low level assembly before we move to the next higher level of assembly. But in the end, it's very difficult to test web in its full up condition like it's going to be in space. It's just trying to duplicate all the thermal boundary conditions, and of course you can't eliminate gravity. You put this thing in a vacuum chamber, suck all the air out, and run liquid nitrogen, cold healing gas along the walls of the inside of the vacuum chamber and get this thing cold, but you can't get rid of gravity, and it's hard to duplicate the thermal boundary conditions perfectly at the entire observatory level. So it's really impractical and infeasible to test the entire observatory all in one piece, and all its test all its functions all at once at one time at that level. So the verification story is kind of one of a lot of puzzle pieces that you put together, and you need analysis to kind of stitch together, connect the dots of the actual test measurements you make. And you have to design with enough margin to cover your uncertainties, which are not only uncertainties in the design and uncertainties when you connect this dot with that dot, but also the uncertainties intrinsic to the tools that you're using to measure with. So it gets complicated to do the verification story. It's not like in the old days or even today when if you've got a satellite that's small, you can say it's the size of a car, you test it all as one piece, pretty much test all its functions in a vacuum chamber and try it all out all at once. But even with things like that, you can't do everything at the same time. But web's a stretch in terms of you do have to kind of piece things together more than would with a smaller satellite, and that makes verification tough. And then lump on top of that the fact that the things that are cold, we have to test them at very, very cold temperatures. Make our measurements there, just need to put in the test equipment that make our measurements there, just need to put in the test equipment that flight to the existing web are quite a task in itself. So there's a lot to that. So those are the engineering challenges: temperature, deployment, and verification. So this is my last slide, just some things to think about. Building this machine is one of the world's greatest engineering challenges today. It's the biggest science project at NASA. It's one of the biggest science projects in the world. And like Hubble before it certainly promises to make amazing discoveries. Hubble was designed to help measure the age, size and age of the universe. That's part of why it was named after Edwin Hubble. And but it's made some amazing discoveries that nobody thought about it, that it would be able to make. Basically answers to questions nobody thought to ask. Some of the greatest discoveries of Hubble were those. And then certainly whenever we look at nature using a new tool of new and powerful capabilities, one like Hubble or like JWST, we always discover amazing things. And that's the promise of this James Webb Space Telescope. And that's what makes it, one of the reasons it makes it so exciting to work on. So that's my presentation. Sorry I talked so much, but I'd be very happy to answer any questions. questions or try to address anything that might help your project. So.
Thank you so much, Paul, for all of that information. I'm sure it's going to take them a bit to absorb it, but I think we should have some questions. Yes, and Dave is saying, please type your questions in so that we can all see them and Paul will answer them.
As it has, is we spent the first several years just inventing the things necessary to make. One obvious one is the mirrors, designing them, and there's a couple aspects about the mirrors. So one, designing mirror segments that we could move and position with the kind of precision I've talked about, and that would be the right shape every time we cool them down from room temperature. That was a pretty big effort. So, and these mirror segments are actually made of beryllium, which is a really light, not very dense, very stiff metal. I think beryllium's number 4 on the periodic table. So, but it's lighter than aluminum and it's very stiff, and but it's got some nasty. It doesn't cast well, and you can't really forge it. So developing the technology to manufacture it was a big deal. So we actually make it we grind beryllium up into make it pure, then grind it up into micro-sized spheres of very uniform size. And then we pour that powder in a can and stick that can in a pressure chamber, and we basically squeeze and heat the can to fuse all the particles together, and that's so that we control the grain structure of the material. So if you just took beryllium, melted it, and poured it to cast it, the grain structure would be very uncontrolled and very inhomogeneous, and so when it changes temperature, its shape changes a lot, and the grain structure will even change with repeated thermal cycles. So to make mirrors out of that, it doesn't work unless you grind it up in the powder and control the grain size at the microscopic level. And we ended up with beryllium instead of glass because beryllium does change shape a lot with temperature, but once you get below 100 Kelvin, it stops changing shape. And we developed a couple of different mirror technologies, and beryllium was one, and a couple different ways to use glass were others. And we ended up not using glass and choosing beryllium, even though beryllium was harder to make. A beryllium mirror, the glass, even with the formulations we developed so that they change very little with temperature and they polish well and would be repeatable, they still would change a little bit with temperature, and even a degree or two of temperature change as you point the telescope one way or another, and your angle to the sun's a little bit different, so the heat coming through the sun shield and the way the thermal distortions in the system change a little bit. It doesn't take much when your air budget is billionths of a meter to you'd be in a mode where you're always trying to tune up the telescope again. So just developing the beryllium mirror technology and then the technology to line up all those mirrors together so they work as one big mirror. Developing those algorithms and testing them. So that's one big technology. Another one was the really lightweight, stable cryogenic structures. So we ended up developing some very specialized carbon graphite epoxy formulations and structures that hold the mirrors and the instruments. Stuff that's very lightweight and very stiff, and changes very little with temperature, and changes very repeatably with temperature. So that's another technology. We extended the state-of-the-art, didn't invent new detector technology, but we extended the state-of-the-art to develop really, really sensitive, low-noise infrared detectors, so that that for every, say, 100 photons of mid-infrared light that hit them, only one electron gets generated that's noise, that's not from directly from those photons that are the ones we really want to detect. And that's really hard to do. And then actually one of our 4 instruments, when I mean instruments, I'm talking cameras and spectrometers. So one of the 4 instruments that we have sees what we call mid-infrared, so wavelengths of light between 5 and 28 microns, and the other 3 instruments see 0.6 to 5 microns. So they see like red visible light out to sort of the near-infrared. And that mid-infrared instrument, its detector technology is different because it detects longer wavelengths of light, and it needs to be like 7 Kelvin, not 37 Kelvin to work. So we had to develop a little refrigerator that can cool from room temperature down to 6 Kelvin to cool the detectors and head instruments so that they work. The rest of the cold party observatory is passively cooled by just radiating heat to deep space, but the detectors in that one mid-infrared instrument need a little refrigerator that uses helium as a working fluid instead of something like Freon or ammonia to cool it down to 6 Kelvin. And that's been a real challenge to develop that thing. There's a few others, but yeah, we had to either invent things from scratch or extend the state of the art on several things. And of course, the whole deployment thing. There have been large structures deployed in space before, like parts of space station use technology called astromast, and really big surveillance satellites that eavesdrop. They use really big antennas that use very lightweight, big structures that deploy antennas. But the kind of the magnitude and scope of what we're doing is the complexity is new. So just developing the mechanisms and the release devices for this thing those are some inventions and technology that got developed for this. So sorry for the long answer, but yeah, a real range of stuff that we had to develop to make this thing feasible, and that's just some of them. Are these new technologies in the public domain? Yeah, one of the nice things about working on this is, as opposed to say something classified as, the technology is available to the public. I mean, there's some proprietary stuff about it from the people that invented it and want to maybe commercialize it and sell it for other things. But yes, there's a lot of information out there about the technologies we've developed that you can just go and find in the public domain. That's cool. Here's a question about air budgets. So, are there any special steps that the engineering team to protect J-based just like yes. So, certainly it's an engineering challenge to design something that's really lightweight, but also very strong and stiff, or strong and resilient. So, that's hard, but actually the biggest mechanical stress of the cold structure is from temperature cool down, because it tries, as it shrinks, the glue that holds the different composite tubes together, the glue and the composite shrink at slightly different rates, so that the thing sees the most stress from cool down than it does from the shaking during launch. But it is, being in the stowed configuration, you can make all your mechanical load paths a lot stronger than they are when it's deployed. And certainly when it's deployed in space and it's in a weightless environment, it doesn't have to hold up its own weight, and so that's no big deal. So, but yeah, in the stowed configuration, the mechanical paths for mechanical loads from the acceleration of the rocket and the shaking from the rocket, it's a pretty strong structure when it's in its stowed condition. And a lot of our strength margins, strength requirements for all the structures, and are from that. And the 5 layers of the sun shield are folded up in a particular fashion and held down with over 100 little tiny pin puller kind of devices to control them and make sure they don't billow as air escapes from them as the rocket goes up, and so they don't flap around and hit the mirrors. The mirrors themselves are actually naked, so to speak, during launch. So, but they're okay because there's nothing to really hit them, and we make sure the inside of the nose cone is clean before it's launched. So, and then all our stuff as we're processing it on the ground, and even once it's in the nose cone of the rocket, we do what we call purging. We keep them in clean rooms, and sometimes we put them inside big plastic bags, basically, and then run pure dry nitrogen or dry air through them to keep them really clean and control the moisture and things like that. So those are things we do to make sure that things are clean and that things structurally are good. The mirrors can move around a little bit when we deploy them off their snubbers. They're actually kind of help. We run those little actuators on those mirror segments all the way to one edge of the range, and the mirrors sit on like snubbers, like little rubber fingers for launch. And that helps with the launch environment. And then when we deploy them in space, and they come off those snubbers, that's where a lot of that 1 millimeter plus range of moving those mirrors around comes from. Is that takes into account any shifts and structural changes over this really big structure that might happen from launch, and we still have the range to move the mirrors and get them all lined up. So hopefully that answers that question. Let's see, were there any specific technologies in particular that be borrowed or substantially improved? Nanometer position, similar, photolithography. Yes, so like the detector technologies were an evolutionary improvement. The precision nanometer mirrors that the actuators that we had. I don't know about photolithography to know, but those little devices are kind of clever because they're basically piezoelectric devices, and then you use lots of levers and gears to amplify their motion so that we can get big amounts of movement, big being a few millimeters, but very fine precision at the same time. I wish I could tell you more about silicon chip manufacturing to compare it, but I really don't know a whole lot about silicon chip manufacturing, honestly. Although I know the contamination requirements for silicon chip manufacturing are make us look dirty. Those are really high cleanliness requirements that they don't have contamination defects at the nano level. But yeah, I wish I could compare it because I don't know about photolithography. But the little mechanisms we came up with are kind of very clever mechanical devices, so that we get a lot of range and high precision at the same time. Okay. Any other questions?
I have a question.
Okay.
Bitch,
Well,
come on.
okay, I'll ask it. Have you developed new technologies in order to make it possible for you to test your materials at cryogenic temperatures?
Okay, say that again. I'm sorry, I was reading Zach's question at the same time I was trying to listen to yours, and I shouldn't have done that. So can you repeat yours, and I'll answer Zach's after I answer you. Okay, so have we come up with new technologies? Got it. Have we come up with new technologies to test materials at cryo? Yeah, actually, there's one thing comes to mind, and I don't know that much about it because it's hard. I wasn't the inventor, but a thing called a speckle interferometer. So, we use interferometers to do a lot of precision measuring of, say, the mirror surfaces. We came up with this thing called a speckle interferometer to measure our precision structures. And what it is, I mean, interferometer just uses interference of light to see. You can measure really, really fine levels, really small levels of shape change and position change with interferometry. So, speckle interferometer is basically an interferometer that takes lots of really fast snapshots. And the idea is that you can hear me now.
Yes, sir. Yes, sir.
Oh, great.
All right,
Okay.
thank you.
We're back. I guess my machine hung up. Sorry. So I just kept talking, so I don't know where where I you stopped hearing me. I was answering the question about test equipment, and then I started answering Zach's question. So just let me know where you want me to pick back up.
I think Zach's question is most important.
Okay. Yeah, so he was asking about the Shack Hartman, and that's basically a technique for helping us line up. That's part of what we use to tell us that the primary mirror segments are lined up relative to each other correctly. So we're actually measuring across the edges. We're measuring little sub-apertures across the edges of the different mirrors, and we're trying to it's kind of like an interference technique to try to see if the edges are lined up correctly. It's one thing to line up the mirrors, and, like, their shape is right and you got them lined up right, but you can imagine that if you're one wavelength out, phase is hard. So like one mirror could be 2 pi or exactly one wavelength out of phase with another one, but it might but that would be hard to tell. So you get this ambiguity because you're looking at differences in waves. And so Shack Hartman is just a way to look across the edges of adjacent mirrors and try to take out that 2 pi or one wavelength ambiguity. And I'm not smart enough anymore on how the details of how Shack Hartman works. So hopefully you can just look that up. But that's part of the suite of techniques we use to get the primary mirror segments lined up so that they're all lined up along the same big hyperbolic surface. It's a real simple way to think of it. So I hope that answers that. I wish I could tell you more about Shack Hartman. It's useful. I got a buddy of mine that is a dyed-in-the-wool optics guy who could tell you a lot more about it. So sorry I'm not that good at that. Cool. And then, but yeah, the one thing I was answering Margaret's question was basically, the real short answer is just the test equipment we've had to develop to be able to test the real thing has been a real challenge. And this thing called speckle interferometry was one thing that was I don't know if it was already invented or we kind of stumbled on and were the first to use it or what, but speckle interferometry was something. I think it was basically just an idea on somebody's research paper, and we kind of actually implemented it to measure how our structures look, whether in the right shape and in the right place. And it's a way to filter out all the noise, background noise that we have in our measuring environment. People moving around, air moving around, trucks moving around outside a quarter mile away. Those things are all noise sources that you can actually see when you're trying to measure things at billionths of a meter. So, yeah, we've developed technology just to make our test equipment feasible. The kind of test equipment we need to test this flight observatory. So that was the answer to that. But yeah, got any more questions? I'll try to.
Well, we may have filled the team leaders. Good. Another question from John. Please go. That is a question for Sharon. Dave, are you able to address that question?
That, that is definitely a Sharon question. I'm the technical guy back here. Pay no attention to the man behind the curtain guy back here.
I do not believe that you are limited. It's just the placement of the icons. It's just the placement of the icons. I think if you cross-reference with the materials that are available, you'll get the answer. Okay, I think we should thank Paul Geithner and Maggie for coming in today. And if you have further questions, send them through Sharon. And I know that Paul will be happy to try and help you get the answers that you seek.
Hey, it was my pleasure. And I was just telling Maggie I've got some other detailed stuff I could send that she could send you. Kind of some engineering details that might be interesting. Because I was just kind of scratching the surface and doing a lot of talking, but there's some more detail I could send you that's still high level, but it's pretty interesting stuff in the engineering standpoint, so I could send you that. And if it's useful, great. If not, hopefully it's just interesting. But I enjoyed it, so it's my pleasure.
Yeah, maybe if you just forward it to Sharon, she can disperse it among the teams, Paul. That would be wonderful.
Okay, will do.
Okay, thanks everyone for coming, and look forward to getting your notices about the next information session. And good luck on your challenge. Have a nice evening.
And I believe this session is videoed for future reference for people that were not able to view it live. So you'll definitely want to mention that to your team members.
All right, bye everybody. Good luck.